By the way, do you like this paper or not?
We haven't do that in 189G, but I think this paper is very interesting, but also very hard, in some
There's some
sense.
details there.
Yeah, a lot of detail. Let me just start my video also.
This one is very similar to a GAN model we discussed before in the
Yeah,
last quarter.
yes. I also incorporate some of your slides from again
Okay,
in
that's
my
good. But this one
PowerPoint.
is more complicated than GAN. The generator seems to incorporate more
Many more
information.
needed, many more. So I don't really think like I think we have like inputted some noise for the GAN, but I don't think that this one is kind of like very similar to GAN, like 100% similar. They are like much more advanced.
Yeah. They incorporate more things into the model.
Yeah.
Okay, so probably we can start. And so today we'll discuss a paper. It's called Giraffe, and presenter will be Zhou Henli, right? And the paper actually is also the CVPR best paper in the last year. And Zhou Hen is actually an undergraduate student in UC Davis, and he will help us discuss this paper. So if anyone in the class who is very familiar with the visions, then you can also contribute more to the discussion of today's talk. Right? Yeah, so Zhou Hen, I will give the time to you, and you can start when you're ready.
Okay, thank you so much, Professor John. So hi everyone, I'm Johan, and today I'm going to present this giraffe paper, and it is actually CVPR 2021 Best Paper Award. So I think it's very interesting for how this paper is really working here, and I'm going to introduce it. So firstly, I'm going to also like if you have any questions or want to join the discussion or interrupt me, just do so. Type in chat or just open your mic. It's okay. So let's first introduce some background. This is Generative Adversary Net or GAN. So the basic idea of the GAN is just like it could generate some unseen photos. So there are some popular results like coming out maybe later. I will show you show them later. So GAN it has two parts. Oops. So basically for the GAN, the illustration of GAN is just like that. So I have a generated data, which is basically generated by the GAN model itself, but it actually come from nothing, like it come from a complete noise. And there is also a discriminator, which is part here, which discriminated fake or real. And we inputted them with real data, with the real images. The data set is actually real data. So how the GAN's training is actually when you are when the generator is generating more data, it goes to discriminator, and discriminator will tell like how fake or real it is compared to real data in some sense. So after the generation of that, like many steps after that, once the discriminator itself is also evolving, but also the generator itself is also evolving. So one explanation of that might be a game. So a game is like the game in economics, or like they have a min max comparison, like kind of like games there. So actually, the discriminator became better in determining fake or real, but the generator would also generate more real photo to cheat the discriminator. And after the process of that, it will finally became real for the generated data. So any question about that at these stages? Or are you familiar with GAN? Or I would just go further. Okay, so I guess no questions. So this is part of discriminator. So as I said before, so the random input. So just to show, like, can you see the my mouse here? Like it is here, right? So the random input is actually just a bunch of noise. So it's kind of like it doesn't mean anything, just like complete like noise, and the noise will come to generator and going to sample here and then send to discriminator. But here we also have real images and sampling from discriminator here. So the discriminator loss would be the loss function of these stages, and the backpropagation would give them parameters to update themselves. And these stages, discriminator would be better and better to determine real and or fake photo. So I think it's pretty much like a classifier here. So it's like a classifier with true or false at discriminator side. And for the another side is the generator side. So here discriminator moved down here a little bit. So it more became like the generator come to the sample trying to cheat the discriminator and generates the generator loss. So if the discriminator could determine that, then it's not a sign that the generator generates better photos to cheat the discriminator. So the backpropagation move like backward and just update all the parameters trying to cheat the discriminator. And here, like we can see, like there are two stages, which discriminator became better and generator became better. And after this process, both of them became very better in the stage of determining the fake and generate the fake. And after all this process, we can generate some very astonishing results. So let's see some of the results back. So actually, GAN model itself, as I see many research about, cannot like generate a very good images by itself, like by this very naive framework itself. So there are many variations of GAN which can give some astonishing results. So the models I show here is not actually based on the this naive model I showed. They have some many variations to create the application size applications. So this is style GAN by NVIDIA. I think it's a couple years ago. So what they do is like with the dataset, car dataset, cat dataset, and also faces dataset, they could actually manage to give a lot of the samples which are not existed before. So all of these photos here, all these cars or cats or faces, they're not existing in the world. They are all completely generated by GAN through kind of like process I mentioned before. So I think it's very astonishing, right, for the style GAN. So they could manage to do that. Any comments on that, or shall I continue? Okay. And this is actually from Professor Zhang in ECS 189G. So this is a sketch image where you just give them input. You have a ground truth and it generates the output, which mimic the input but completely different than the truth. Kind of similar here is like, I think it's more like an NLP with scan. So you have text to image, while you say the flower is white and pink in color or something, and it generated some photos back in different GAN approaches. So I think here this text to image dataset kind of give us a sense of why we want the 3D scan GAN, because like we really wanted some feature to be changed. We wanted to generate some feature out. So as we can see, like beforehand, we don't have much control in the generated process. What we do is we feed it with real input, like real data sets, and also feed them with noises, and let the model itself to figure out what to generate. So we don't really have control in the generated process. So just to imagine how good we could achieve if we finally achieve, like we could control what part to generate instead of like only let the model to figure out by itself. So let's watch a video from Unreal Engine 5. So as you can see, these like videos we have seen actually come from a lot of I don't know what was their title, maybe designer, game designer, or game player, which like they manage the Unreal Engine 5, which is basically like a scene creator or something. Like they have to like do a lot of job, like maybe 10 hours or more, like hundreds of hours job to just create a scene we just have seen. So imagine like if we could actually controlling uh, different stages of generating process. Like we could maybe like maybe like tell the AI someday to like maybe we can change the background, move the character, or add more a character in one scene, and that will definitely give us the future of GAN. Like it's kind of where like why GANs existed. Like we don't only satisfied with the photos we generated, but we're also excited about like maybe we could finally one day generating video thing, or even more of them to the real world. So as that as our consideration, let me introduce you some popular way to do 3D representation in GAN. So as we can see here, we have Platonic GAN, and we have also Holo GAN, and also a very mature version of GIRAFFE proposed by the same research group, the Max Planck Institute of Intelligence. So here they have different comparison between these three methods of 3D representations. So as we can see, Platonic GAN, they use a representation model called voxel representation. If I understand correctly, like this is basically like they kind of like sampling them like in the photo side, not like they create this sample with different poses. Like that's basically what I'm figuring out at this time. So hologram and Platonic GANs take the same voxel representation but in different approaches. So Platonic GAN, they use the photos they sampled from different poses and like trying to combine them into one 3D object and render them uh, afterward. So in this part, I think the problem here, like if you can see the rendered photo. Oh, sorry. So the problem is really like they have a consistent images, but their accuracy was not that precise. You could see like this is very fluent construction. Like you can see they're all attached. They're very consistent, but the very precision of that, like how it uh, represents, like how it mimics a real car, were not that good in some of the detailed parts. But for the hologram, they use 3D features, which I think like they created feature by feature, I guess, and using neural rendering, and they finally achieved the part which they have very good precision. Like you can see, like every part where it successfully generated has a part like a car, but the consistency itself, like it's not very continuous, and I think that generates some problem. So based on those two 3D representation approaches, would give a lot of burden into the world we imagine. The Max Planck Institute of Intelligence, they propose new way using generative radiance fields for the 3D well image synthesis. So I kind of a little bit hard to like actually explain the like how the radiance fields are represented, but as I have a kind of fields, it's more like you have a static photo like poses. Like you have a imaginary camera thing, and you just have a vector viewing the object in different viewpoints, and given like I would think like this give you more parameters to learn, so they could finally rendering a more consistent and more accurate car in the end. So I feel like maybe it's hard to explain in words. So I also turns on a Unity sample like here to show like how they might do that. So I think what the radiance field really means is like imagine here is a vector, and this is the distance between this and also the directions. So this is a one camera point. This is my camera. So I can do this to move up and this to move down. Also the radiance field will give us some kind of parameters, like we can characterize them or quantify them with the distance between object and my viewpoint. I can also turn them in, turn them out, and turn left or turn right as my parameters are changing, and they take them in different angles. Like I can also do these angles and different camera viewpoints and my position to that. They sample all of them and get to the final output of them. However, I think when they're doing that, and this is the generated radiance fields. So I think when they're doing that, they face some problems here. So as their model was not as a giraffe, like I think let me just maybe first go through their masters, and let's discuss what the drawbacks of this GRAF, generated radiance field, for 3D aware image synthesis. So at this part, I think what they do is like as I previously seen, like they have a resampling, like they do kind of like vector, to represent the position of camera and also where the camera the car sings at, and they give them a bunch of parameter like gamma, xri here, and also they put them into a conditional radiance field to generate color and density, and they do volume rendering and afterward generates pictures of cars. So I think the main difference between here and giraffe is that actually in the part of conditional radiance fields, as I will talk to them later. I'll have some more detailed explanation afterward. So at first, maybe let's just first discuss about resampling. So as I discussed about like the resampling, I think is basically you have a consistent camera viewpoint, but you sample out like the features, like maybe the features of one images in different viewpoints at these stages. And you have and I think here the kind of like E symbol here represents different camera points, like the viewpoints of them, and the K is representing the camera matrix. And the V, I'm not very sure about what they are representing here, but if you have any comments, please comment on them. And that's how the giraffe, GRAF, they're doing here, and they are in their approach. They have different sample outs, the different like features of one images. And afterward that they have a DR ray, gamma ray, and also I think gamma ray is just like a field representation, like a vectors consistent with colors. And afterward that they put them into a fully connected MLPs with a ReLU activation, and they just giving out colors and their densities. After volume rendering, they then recreated one generated images based on colors and given to the discriminator, and just giving the similar approach as we were talking about in GET, and generating some new photos. But I think in that part, I think maybe you can see at this point like they don't actually given many controls over the generated process. And although they have a 3D awareness, like they have a conditional radiance field represented by vectors, but it don't really like having some novelties out. I think if you're feeling that part, you are on the correct position, because that's some of the result of giraffe. That's because of like I think that let's do some evaluation on giraffe. So it's like it's a very novel method for 3D real image synthesis, and they have a high resolution multi-view consistent image generation, as the results show. Like you can see here, it's kind of like consistent. Like so, the consistency is basically means like they have like cars. Every part of the car, likes car, is very consistent in some sense. Not like they don't have like the break points which they break down. And it's pretty amazing job here, but they don't have the ability like we were trying to approach to, so they don't have power to rotate or anything. So it's just like static 3D images, 2D images with like 3D awareness, rather than like real 3D like 3D sense of 2D images. Like you can have a different cars in different angles. So and this can be trained from row on post position on post photos. I think the on post row on post photos here basically means like you don't sample out different different like viewpoints at that sense. So the viewpoint we were talking about is only like controlled by the model itself, controlled by the computers itself. So we only input them with raw like unchanged photo, but the like different angles will be generated by computers to find out like the different viewpoints, and also so giving them different viewpoints and the distance between them. That's kind of a novelty for the GRAF. And it also demonstrates like radiance field, like we will talk about like the vector things, can be a very effective representation of a generative task. And in other words, basically says like for the generated task, if you give them 3D awareness of giving the model 3D awareness, it would be very good to effectively generate more results, like more static, like 3D view of 2D, like different angles of 2D images of a car, something like that. But it also have limitation. So it's limited to the single object things, and it'll also have slow rendering time. So the slow rendering time, as I guess here, could be explained that you are giving them the value rendering part. You're giving them color images. You're giving them RGB images generated by conditional radiance field, and that would definitely give you like, it's a three it's 3 layers of photos in some sense, and it definitely give you like very slow rendering time. Just wait a moment. So let's just do a quick comparison between what we have learned about GIRAFFE in the paper and also about GRAF. So the GRAF is really 3D representation into generated models. But GIRAFFE, they're a compositional 3D scene representation into generative model. So in other words, GIRAFFE, like they take different, not only color, but different features as their consideration. And we'll see why in a minute. And before that, I will do some explanation about NERV. And this is actually a video. So Professor Zhang, do you know can you hear the sound before I show the video? Or
Yes, I can hear those sounds.
okay,
Okay.
that's good because it's a video. So that's basically what NERV can do. It's like they have different viewpoints. They can rotate. So let's see how they achieve that.
We present neural radiance fields, or NERF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we're able to optimize this scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. We first show comparisons to top-performing methods on synthetically rendered data. Scene representation networks implicitly represent a scene using a fully connected neural network. SRNs have issues with multi-view consistency and are unable to represent high-frequency details. Local light field fusion uses a pre-trained network to promote each input view to a high-resolution 3D volume. Inconsistencies between adjacent volumes causes flickering artifacts. Neural volumes encode a scene as a 128 cubed voxel grid and use a warp field to better allocate these limited samples. However, they're still unable to represent high-resolution content, such as the fine details in the ship's texture and rigging. We see the same trend in all of our synthetic test scenes. Our method both qualitatively and quantitatively outperforms the other methods. Here we show the results of our method on the 6 other objects in our realistically rendered dataset with complex geometry and non-Lambertian materials. Next, we will show comparisons on real scenes captured with a forward-facing phone camera. SRN uses a recurrent network to ray march through encoded scenes, resulting in an inconsistent appearance between rendered views. LLFF blends between multiple renderings with different limited fields of view, resulting in flickering artifacts along image borders. Here, only our method can represent fine details with complex occlusion effects, such as the ribs in this fossilized T-Rex skeleton. Now let's take a look at some additional real results. We can visualize the view-dependent effects captured by our representation, such as the semi-transparent appearance of the olive oil bottle and specularities on the stove, reflections on this room's television and specularities on the conference table, and sharp reflections and specularities on this red car's body and windshield. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusions in the Christmas tree leaves and ornaments. This geometry is precise enough to be used for additional graphics applications, such as virtual object insertion with convincing occlusion effects. Here, we visualize additional results across a wide variety of real-world scenes, each captured with only 20 to 50 input images. Our neural radiance field representations are able to render photorealistic novel views of entire scenes with fine geometry details and realistic view-dependent reflectance effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network. We also show preliminary results for 360-degree capture of real scenes.
Okay, so that's the nerve is about. So let's get back to giraffe, and I'm going to talk about why nerve is very important for the giraffe. So for giraffe, this is the pretty much like the simplest overview of that. So it's like have latent code and go into the generator, which encrypts the 3D scene structure and finally generates a generated photo images, which can change background or rotate. That's how giraffe is. And I'm characterized giraffe. This is not 100% true, but I will just characterize giraffe as a combination of nerve and GIRAFFE. So as we were seeing just a moment ago about nerve, so I think the novelty of them is like it avoids the generated photo by sampling RGB colors. Like you can see like the given 5 parameters, X, Y, Z, and also 2 others. They are basically giving position and viewpoints of different images, and by that sense, it just eliminates the RGB colors representation or parameters in the input, but the in another way, giving fully connected layers, and let the fully connected layer decide what RGB color and density to outputs in the generated 2D photos. And it's, I think giraffe definitely incorporated some idea from that in the neural rendering part and also in the whole architecture. And I think that's why nerve is very important for the achievement of the giraffe. And for the for the giraffe, and for the GIRAFFE, the giraffe part, the larger model were actually very similar to GIRAFFE, but they just changed some part like conditional radiance fields and added one more neural render part to the model, and it just like modified the GIRAFFE with some idea of nerve and finally achieved giraffe. So this is more simpler architecture of giraffe before we move to the very complicated one on the paper. So here in the sample feature fields in the downside, the giraffe. So in the sample feature fields, I think one novelty in giraffe is like they are not like giving a lot of samples together and generating photos. Instead, they're giving like one single photo a chance like to go through the post feature fields and finally generating volume rendering of feature images. And they also separated the object and the background. So as you can see, H1 and H2, they're basically objects in a data set. And HN, like only HN, they're doing the background inside them. So they kind of separated the background and objects in the training part instead of incorporating them and giving all of them to do resampling or 3D point sampling as if in the GRAF. And that part will give you a sense, some control over the model to actively change the background or added objects to one scene. And one thing to notice here is like I think he said it, the author said it in the presentation, like the background itself is actually fixed, so they don't give in any more background in one data set to the model. So they only have one fixed background in every iterations of training, and that's the basic idea of GIRAFFE. And in the post feature fields, I think what they effectively do is I think they change the RGB value representation to more like a neural feature fields representation as NERV is doing. So instead, so what's basically saying is like instead of RGB intensity values, they change them to the XYZ and kind of like viewpoints and also the different vectors in the post feature field. So they neglected the RGB part when in the feature fields, and afterward, when they go into the volume rendering of feature images, they put the features together as the feature images in different camera viewpoints and generating not a feature image, like 3D representation of feature images out. And then finally, they feed the 3D images photos to the 2D CNN decoder. And that 2D CNN decoder is very much like the part in the left top part where you have an output of color plus density. So that's basically the decoder or the 2D CNN would generate RGB image color that we see from the XYZ directions as of the camera are moving from each other from parts and generates this out as an output image. That's kind of the idea of GIRAFFE. So let's view this this very terrifying 3D scene compositions. As the inputs, they have this is basically GIRAFFE's architecture. So as of the input sample camera's poses and do recastling, kind of like in the GRAF, which is the red right top part, but they also like they separate them to gamma DJ and gamma XIJ to represent I suppose it represents different viewpoints and different position of X and Y. And then you give them to the generative neural feature fields, which basically I think is just like H1, H2, and Hn in the sample feature fields like that. Like the sample out a lot of objects and background out. And then after the feature fields, please see the left down part here in neural feature fields. So those 4D four parameters would then go through the fully connected MLP like here, and then generated two results, which is F and the density. I think at that part is only giving us the feature vector and density. So so it's more like as you can see here, it neglects the the representation of RGBs with only the vector we talk about and the densities in each part. And then since like every like in each neutral feature fields, they have one density and one feature vector. They have to figure out a way to combine them together and generate the photo, and to go through the volume rendering and then generate a real photo. So I think they have some simple operators here called composition operator. And as you can see here in the bottom mid part, so they have n feature fields, which is just like the different H1, H2, Hn sample feature fields there, and they figure out the way to put them together. So here they using the final density, which is like the sum of all the densities, and they then find a final feature vector representation by multiplying each vector with densities and then sample out, then average them with the mean density. I think I'm not very sure like why this is very trivial, or but I think as for the formula, I'm not very like know what is significant, but I think they explained it, but not very in detail. I guess it might be like I'm not really knowledge in have a lot of knowledge in the function, but I guess in that sense they will sample out all the average densities and the feature vector, and will give kind of like a multi layers of photos to be generated as a 3D scene. So I don't know if anyone have any comments on here, because you can maybe share it if you have a better understanding, and we can move to the next part of volume rendering. So any comments on here? Okay. Okay, so I will maybe move forward. So in the volume rendering part, as I previously talked about, so they have now densities and also some like a final feature vectors, and what they wanted to do is like put it into the volume rendering part and give it a 3D sense of different positions, as I may recall, and then generates to FJ, like which is another feature vectors, like giving the 3D sense and give it into the neural render. So the neural render, as you can see in the right left part and in the right bottom part, is basically a convolution layer with ReLU activation. So so maybe we could think this as a black box, and after the final feature vector goes in, it will generate it as a 2D image. 2D image is instead of 3D image. So in another word, so the feature images like without the sense of color, after the decoder of 2D CNNs, it would output the images which resembles like that, and it also the part which the like the representation of neural feature fields would match to the color and give them a sense of what the output images are. So I guess in that part, the sample feature fields, like all of them, since they have sampled out different objects, they could effectively adding sense to that. Like now we don't need to bother of colors. We only represent things by their positions and also their viewpoints. And in that sense, we can definitely add what we want and to change the rotation of them by what we want, and then match them by a fully connected CNN MLN plus, I guess it's a MLP plus CNN neural networks, and giving them giving them a color of that instead of giving color at the first time. So I think that would definitely give the control in sense by adding objects and matching the backgrounds. But another advantage I could think of is also since they're having decode like feature images and like feature images as 3D representation and match them to the colors in the 2D sense, I think in that part it also largely decreases the computational power needs for generating such images. So previously in the GRAF, they just all of them were colored images, so they need and they make the color images to a 3D representation, and then they move into decoder and giving the samples out. I think that would definitely have needed a lot of computing powers in this one, which only have a feature images and then having a decoder to match the color of them and back to the output images. So I think that's the two main advantage of GIRAFFE in the sense. So it giving the free control of the generated part, but it's also giving like largely decrease the rendering time of generating such photos. And this is the GIRAFFE vs GIRAFFE. I don't know how to pronounce that, GRAF. So as you can see, it's just like they have different conditional radiance field, have different inputs. So now they don't need to concern about the camera matrix. They only need to like having sample camera poses to do this amazing job. And they also added a neural render and a composition operator to of all the generative neural feature fields, and that would I would think compared to GRAF, it's just like the elimination of color in the training process is definitely giving some shorten the render time in some sense. And this is conditional fields with feature fields. So I think conditional fields are only like with bunch of MLPs, but also I mean also the feature fields is a bunch of MLPs, but they're generating different things. Like here we have color hat and density hat, but for the feature fields, our output is actually density and feature field, like or feature hat instead of color hat. So the elimination of color here really just giving a lot of control. And let's see the results. So this is their website on GitHub. So if you're interested, I also incorporated in the reference. Just I don't think I have a great job selling all of them, but you can definitely watch the video, their talks, and give you more sense. And this is their results. This is the comparison against the 2D base GAN. So as you can see here, like 2D base GAN, they're just like bouncing around, changing, like even change the objects in that sense. So it's not a very smooth output. But our master here, they can do this very smoothly. Although you can see here the color were not that accurate, like it has some changes, but you can see like the object here is very consistent and the part is also very smooth. And here the circular translation, they also have some very good results. And here is the objects. And before that, because of like we separate the background and the objects, we can now doing some controllable scene generation, which different poses of the object without changing the background. So if we do the like previous like we don't separate the background out, that would definitely give us some like we can now do this wonderful controllable scene generation. And same here with the faces with rotate objects. And now what's more exciting about GIRAFFE is like it also have some control over the like this photo they never seen by the neural network, but here they could also like predict like what would be like when it's out of bounds. So it's also very exciting. This is a vertical translation. And this is the change object appearance. This is the out of distribution generalization. And you could even add more objects to the thing like that. And this is their citation. Thank you so much for their wonderful jobs. So let's get back to the results, and we haven't seen the results of the generated photos. So let's see how their quantitative results were like. So this is their FID scores at the 4 pixels rendering time. So we can see they have pretty good scores at that sense in both in 64 multiply 64 pixels and also 256 one. And their network parameters were actually much lower than other GANs are needed. So that's this quantitative comparison really shows the superiority of this method. And another very good way of the GIRAFFE is the render time, as we were talking about. So 64 by 64 pixels images generated by GIRAFFE will cost like 110 milliseconds. But here in GIRAFFE, it's only needed 4.8 milliseconds. And that's a really, really significant decrease of rendering time, and that's I would say like it's mostly contributed by the representation of field representation instead of like feature representation instead of the color representation. That would definitely really lower down all the parameter needed to learn and giving a better rendering time. So let's do some evaluation on GIRAFFE. This is a very novel method for 3D controllable image synthesis. So now we have very good control on different things. We can add objects, doing rotation of them, even generate some like out of distribution results. And now it also allows a very high resolution, very consistent image generation. And as GIRAFFE, it also can be trained from raw and unposed image collections, and we have explicit control over single objects. Just like that, we can rotate them, like add more objects on them, so we can have more control on the elements on one generated photo. But also have some drawbacks, like as you can see, the multi-object scenes of low complexity. So when we think about like the Unreal Engine, we think about, so it has like so in the game scenarios have like a grassland, and they have different grass or objects on it on top, and it's have like more orientation, more angles, and more different synthesis of one images. But here in the GIRAFFE, they only have some very naive one. So they only have like in the one play they have different objects on it. So that would definitely the thing like GIRAFFE need to work on in the future. And it also have some inherent biases. So I think the inherent biases comes from the sample part. So if the images have different angles of like only one viewpoint of them, then it will definitely not generate a very good results as I recall. And it also assumed a uniform distribution over camera poses and object level transformation, their real distribution. So it really assumes the camera poses to be a uniform distribution, and they don't really like going to details about the camera poses in their samples, and to like check if that distribution is really true. So they really assume the uniform distribution of the latent code and to generate them, and that may be one of the problem. And I think we have future works. So I think there This is actually from UC Davis. So it's going to be posted on CVPR 2022, and it's a Giraffe HD, which is just a high resolution of Giraffe. I think that's pretty interesting. So if you have time and you feel like very interesting about that, please go check the paper. The results is pretty astonishing. It's pretty HD rather than Giraffe. And this is my reference list. And thank you so much for those wonderful researchers and creators. Without their job, I couldn't even conceive this PowerPoint, this keynote. And please just go check them because they're also very, very good like knowledges, like very good information to really understand this paper, as I'm not a very good explainer, and some part I'm also very confusing many points. And thank you so much for listening.
Okay, the talk actually is very good, and thanks so much. Okay, so any question from the audience?
I have a question.
Yeah, go ahead.
Yeah. So in the paper, I saw when they're comparing it with 2D GAN, their results are like almost similar with that of, not for everybody, just for cats and something else. Their results are very similar to that of giraffe model. Like why is it only for cars it is behaving like that? Like for others the scores are a little different. Is there any reason why it is like that?
I'm actually not very sure, but I think maybe that's because I think like Stelgan, they also have some very good results in a generation of cars. So I guess maybe this essence of the GANs, like it could be better than generates out the car samples rather than others, and maybe like the car samples or data sets are more known by the fields rather than others, but I'm not very sure about that.
Okay, yeah, that was like pretty intriguing. Like, I didn't understand why only for cars and churches it is behaving like this, for others it is okay. So I just
I think it's maybe I think they maybe mentioned it in the presentation. Like you can check the link. I will send it later in the website. Thank you.
Thank you.
I wanted to ask, do you think this approach could be extended to hierarchical scenes, since we just read the Guam paper?
Oh, that's definitely. I have seen a lot of reference. It actually the hierarchical ones that definitely they reference some giraffe things. So I think I'm not very familiar with hierarchical, but I think when I do the research at that, I think it's pretty astonishing. Like the hierarchical has some citation of giraffe. So I think definitely it will have some application to the hierarchical thing that you do.
Cool. Thanks.
Yep.
Yeah, any more questions? Yeah, I'll just check the Giraffe HD paper you mentioned. Actually, this is from Yongjiro. Also, our previous faculty at UC Davis, right?
Oh, yeah.
Yeah.
Wow.
So it's also good. I didn't know this paper yet. I mean, until you introduced this paper in the
Yeah, also like I searched it. It actually submitted very recently. I think it submitted on March 28th or something. So it's like
it's a
a
new
month
paper.
ago. Yes, very new paper to CVPR.
Yeah. So you can see, I mean, new papers coming out every day, right? So we have to update ourselves all the time. Yeah.
Yeah, this always new things coming up.
Yeah. So
I'm surprised.
yeah. Any more questions from the audience? Okay, so if we have, that's it for today. And the talk is very good. And thanks so much, Johan. And
Thank you so much. I don't think I do a really good job in explaining many
No, you're doing
things.
very good. You're doing very good. So no worry about that. Also, I mean, for students, also a reminder. So for this course, we have a proposal which will be due in 2 weeks. If I remember correctly, the proposal for the project will be due by the April 29. So you still have 2 weeks to consider the project you can do for the final paper. So I think you have to discuss with your teammates, to decide your project, then also finish the proposal. If, for some of the team, if your proposal has been decided already, then you can go ahead to, implement the models out according to your proposal. And then you can start only, you don't need to rush at the very end. So for the quarter, yeah, this is just a reminder for the proposal, which will be due by the April 29th in this month. Yeah. Okay, so the talk is very good. And this paper is a very interesting paper, right? And let's thank the speakers. Yeah. Thank you.
Yes, thank you very much.
Yeah. So I see one question. Yes, you can write a proposal with the ACM template. We have provided with the template already, and you can download the template. We also mentioned it would be the ACM SIG conference, this kind of template. And if you can write with NetApp, then you can just download this template for your project. Okay, thanks.
Thank you and have a great day. Bye.
You too, thanks. Yeah, bye-bye. By the way, I will host office hours on Monday just after class. So if you have any question or ideas to discuss with me, you can also talk with me after class during office hours.